minus 10, 9, 8, 7.
Thanks. I'd like to start off by talking about ambition, or rather lack of ambition. Sometimes in comics or movies or films, you get supervillains, and their greatest ambition is to take over the world. This is thinking far too small. Some of them think a bit bigger. But again, this is thinking far too small. One galaxy? This is the Hubble ultra-deep field. Every speck of light you see there is a galaxy, and there are about 10,000 galaxies visible total. Is this ambitious enough? Well, not really, but it's a start. I'm going to argue that if the assumptions are true, mass space colonization by humanity is essentially almost inevitable. To do that, I'm going to make use of the methods of experimental engineering. That's basically trying to predict science and technology that is physically possible and is quite probable to exist in the not-too-distant future. So if that blue area represents what we know exists, the red area represents things that we know we can't do, such as going faster than light, then exploratory engineering lies around there. Of course, it's a lot easier to just draw an arrow on a graph than to define what we mean. So what do we mean? Is it sort of robot butlers and teleporters? No. We're not going to sort of turn to literature or just imagination. We need to make some assumptions. First of all, this is a big assumption, but give it to me. Let's assume that humanity survives. Second of all, I'm assuming that we're going to be able to continue to copy nature as we do, which means that we'll be able to co-opt or copy any natural process eventually. So I'm going to assume that some forms of artificial intelligence or replication is possible. And lastly, I'm going to assume that anything we can do, we can automate. Again, this is something that humans have proven very good at. This means that, for instance, building factories is also something that we can automate. With these assumptions, things that seem like obstacles today, like cost or scale, are no longer. For instance, to illustrate scale, some things don't scale. This is a sword that is 400 times bigger than a normal sword. It doesn't make you a 400 times better swordsman if you happen to have it. If you have a woman who can give birth to a baby in 9 months, then having 9 pregnant women doesn't allow you to produce a baby in 1 month. These sort of things don't scale. This does. Silicon chips do very simple things, sort of incredibly basic, dull, simplistic things, except they do it again and again, almost perfectly, very, very fast. And this scales up to the underpinning of the modern economy. And I'm going to argue that space exploration has a lot more in common with silicon chips than it has with the other things that don't scale. The other issue is cost. Now, I don't denigrate costs, and I wish sort of a lot of science fiction authors paid more attention to economics. But economics doesn't mean constant cost. This is Napoleon III, one of the most impressive mustaches to have ever ruled a European country. Back in his era, aluminium was extremely difficult to extract, and he allegedly gave banquets where the richest and most influential of his guests dined on aluminium plates, while the second tier had to make do with gold cutlery. Of course, nowadays, we've mastered other ways of producing aluminium, and now it's just mainly the contents of landfills. So costs can change quite fast. But anyway, back to the main theme. How are we going to colonize the universe? Well, this is sort of the old-fashioned idea, based somewhat on, say, European colonization and discovery. It's the idea that you go somewhere, you rest there, you build up resources, maybe you build up a new generation, and then you continue spreading, and step by step you make your way to your destination or to somewhere else. Let's try something else. Let's go everywhere, all at once. And as soon as we arrive anywhere, let's go everywhere in that galaxy, all at once. To do that, we're going to need to send something that can replicate itself on arrival. These are often called von Neumann probes. What's an example of it? Well, an example of, let's start with a couple. Let's start with many couples, actually. Give them some food, some manufacturing ability, information. You plonk an engine on it so it can move, wrap it all up, and you have your von Neumann probe, otherwise known as a generation spaceship. However, this reproduces only very slowly and has very limited acceleration because of the squishy humans on board. What else can we do? This is the Bracewell-Freitas self-replicating probe, based on the Daedalus probe design and on NASA's self-replicating lunar factory, which they designed in the 1980s. It has basic AI and fusion engines, and it replicates in about 500 years to build another probe. And the actual replicating bit is 500 tons. This is way too heavy, but it's a useful upper bound. And this thing was designed in the 1980s. I think we might be able to do better. How small? Well, I said we can copy nature. This is Vibrio comma. It's 10 to the minus 16 kilograms in weight, which is a scientific and technical term for very, very small. This is also something very interesting. This is an acorn. Why is an acorn interesting? Because, well, an acorn is basically something that builds a solar-powered factory, a solar-powered acorn factory. This is the perfect replicator. The smallest acorn is about 1 gram, so I'm assuming that with some reaction mass, some legs to extract resources, and maybe some nuclear power initially, we could get away with, say, a 30-gram probe, a 30-gram replicator. This arrives, it starts building up copies of itself. Sorry, it starts building up power sources first, and then copies of itself. But, of course, before it gets there, it has to slow down. How are we going to do that? Well, the good old-fashioned way, with rockets. There's lots of exotic other ways you might want to decelerate, but let's ignore them for the moment. This is the relativistic rocket equation. It is rather bastardly. For a final mass of 30 grams, well, how much mass do you need on launch? It depends on what engines you have and how fast you're going. So for 3 different speeds, 50% to 99% of the speed of light, and 3 different engine designs, a matter-antimatter, very science fiction-y, slightly more reasonable fusion engines, and perfectly respectable fission engines. And we're going to look at these 3 scenarios and round up the masses a bit to 5 kilograms, 15 tons, and 35 tons. Those will be our 3 scenarios to look at. Well, I lied when I said that we wouldn't consider any exotic ways of decelerating, because the universe, as far as we can tell, is actually expanding faster and faster. We're entering a more exponential phase of expansion. And this gives a very unique way of decelerating, which is basically don't bother. If you wait long enough and you go for distant galaxies, your probe will have lost all its velocity just naturally upon arrival. So we'll consider that as a 4th scenario. Now, how far can we go? Because of the continuing expansion of the universe, we can't go infinite distance. We can't capture infinitely many galaxies. This is about as far as we can go at 50% of the speed of light. That's the blue line. The purple one is 80%. The green one is 99%. And light itself is the black line for comparison. The distance we can go on the green line is about 4 gigaparsecs, which is probably the longest distance that you've ever heard in your life. At that distance, we can capture about 4 billion galaxies. If we go the slow way with the old-fashioned fission engines, we're restricted to only 100 million. So I've been talking about sending probes very fast and sending out a lot of them. How are we going to power all this? Where in the solar system could we find a source of energy? Well, okay, there's only really one place. Science fiction is full of designs of how to harvest the energy of a sun with, say, Dyson spheres and other similar ideas. The only one that's really practical is the Dyson swarm, which is a lot of independent solar captors surrounding the sun. To do that, we need a convenient source of material very close to the sun, with quite a lot of material. So, as they say, sorry, Mercury, it's nothing personal. The basic idea is start with getting some energy. Put some solar captors on the surface of Mercury. Use them to mine stuff using the automation that we have by assumption. Get that stuff into orbit. And in orbit, make solar collectors and further factories. With this, get more energy and send that back to the beginning of the process. All this is using technology that we already have today, basically, or things we'll have very soon. Under relatively conservative assumptions, one of which is, for instance, that it takes 5 years to construct the solar panels. 6 months would be more realistic, but even under a 5-year assumption, this is how much energy we'll have on a log scale. First, there's no change for 5 years. Then the first generation of new solar captors starts coming online. Then there's a second jump at 10 years as the second generation of solar captors starts coming online. And then it sort of smooths out a bit. Now, why have I not plotted the energy any further than that? Well, that's because the mass of Mercury does this in that time. It takes about 33 years to take the planet apart entirely. Now, this is all due to the exponential nature of the graph that I showed before. As long as you get that cycle, that you can get energy to build more factories, to build more solar panels, to get more energy, and etc., Mercury comes apart in very reasonable amounts of time. If you don't get that cycle, you can't. But that's the kind of things that does tend to scale well. Then once we have our Dyson swarm, we get energy from it, and we use some fixed launching system. Rail guns, quench guns, solar sails with lasers. There's a variety of different ones you can do. Let's put that all together. These are the 4 scenarios. You can look up the numbers more in our paper where we deal with some other issues. What are the total energy requirements for this? Well, they're of the order of 10 to the power 30, which is another technical scientific term for a very big number. And if we have our sun at 10 to the 26 watts and about a third efficiency, how long would it take to get the energy to launch self-replicating probes in multiples to every single galaxy in the universe that we could ever reach? 6 hours in the worst-case scenario. Now, remember I also this is for the 30-gram replicator. Remember that I also talked about the 500-ton replicator as an upper bound. That would take considerably longer, 11,000 years in the worst case. But on the cosmic scale, all these numbers are exactly 0. They're indistinguishable from noise. So if humanity continues to survive and expands through our solar system and maybe through a few new nearby solar systems as a technological species, there will come a time that is insignificant in the cosmic scale, where the mass colonization of the universe will be something that would be very trivial for us to do. Of course, this argument also works in reverse. Here I've plotted the lines going back in time. How many galaxies could have reached us if they had started 1 billion, 2 billion, 3 billion, etc. years ago? And even at a slow speed, there's millions of galaxies that could have reached us. So the fact that we see no alien presence in our galaxy is not, we not only have to worry why we don't see any aliens in our galaxy, we have to worry why we haven't seen any aliens that have crossed over. So the skies are probably a lot emptier than we wish to believe. But some people at this point argue that humanity, or maybe aliens, will just not wish to expand. Why would we want to do this, even if we could? Well, first of all, there's some groups today who want to do it. British Interplanetary Society, they're for it. Certain religious groups might want to do it, certain philosophical groups. There are some, say, oppressed or resentful sub-factions who might want to escape. get away from a dominant faction. And more importantly, maybe the dominant faction doesn't like the idea of groups escaping or expanding. But the only real way of preventing that is to expand yourself and get there first. If humanity expands, we'll be relatively immune from civilization collapse. And this is maybe the most important argument of all. I could imagine that humanity got wise and peaceful and all the good qualities that we'd ever want, and would agree that maybe we shouldn't grab the universe. Maybe it's not for us. However, I cannot imagine humanity being okay with potential aliens grabbing the universe and using it for whatever purposes they might. And this sets up a prisoner's dilemma. The only effective way of stopping an alien species from grabbing the universe is to go and grab the universe yourself. And it's even more urgent to do that because you know they want to grab the universe to stop you from grabbing the universe, the untrustworthy bastards. So you need to grab the universe. So it seems like, so I've argued that it's possible and the motivation will almost certainly be there, especially because you only need to start it once. Say humanity survives 20,000 years and this is possible. You just need to start the expansion once and it's pretty much irrevocable. So, in conclusion, the sky is most definitely not the limit. If we survive, and that's a big if, but if we survive, some humans will likely colonize the universe. Thank you.